Have you ever wondered exactly how much weight it takes to tip over a table? Not just a guess, but the precise minimum mass that physics predicts. In this video, we'll answer that question using a real example. Welcome to Advanced Physics Explained, where challenging problems are broken down step by step. Here, every equation reveals insight, and even the most complex ideas become clear. Let's begin. Here's today's challenge. A circular table, 2 meters in diameter and weighing 20 kilograms, is supported by 3 legs, each 5 kilograms, arranged in an equilateral triangle near the edge. Your task is to find minimum mass that, if placed on the tabletop, will tip the table. Take a moment to pause the video and try solving this on your own. Sketch the table, consider the center of mass, and think about how the tipping point depends on the position of the weight. Once you're ready, press play, and we'll solve it step by step, uncovering the physics behind it. Now let's solve the problem step by step. First, we need to clearly visualize the system. Here's the similar image showing circular table and its 3 supporting legs arranged in an equilateral triangle. But according to the question, legs are supposed to be near the edge of the table. Keep that in mind. Take a close look. This will help us understand how the center of mass and tipping point relate. To make the geometry clear, let's represent the table as a circle of diameter 2 meters. Inside, we place an equilateral triangle whose corners mark the positions of the 3 legs at the edge. We'll call these points A, B, and C. Since the diameter is 2 meters, the radius is simply half, that's 1 meter. Now, to analyze the forces and tipping, we'll place our circle on an XY coordinate plane with the center at the origin. The 3 legs sit on the circumference, so their positions can be described using simple trigonometry. In polar coordinates, any point on the circle of radius r can be written as... Since radius is 1 meter, the formula can be further simplified to... This formula lets us assign exact coordinates to points A, B, and C, spaced equally by 120 degrees. In polar coordinates, angles are always measured from the positive x-axis. If you're wondering what polar coordinate is, it's just another way of locating a point on a flat surface. Instead of giving the horizontal and vertical distances, we describe a point by how far it is from the center, called the radius, and the angle it makes with the positive x-axis. Point C is straight above the center. That means its angle is 90 degrees. Since the 3 legs form an equilateral triangle, the other 2 points must be spaced by 120 degrees around the circle. So, moving 120 degrees clockwise from C gives point A minus 30 degrees by taking 90 degrees minus 120 degrees. And moving 120 degrees counterclockwise gives point B 210 degrees by taking 90 degrees plus 120 degrees. Now we can substitute these angles into our formula to get x and y position of each leg. Next, let's think about the center of mass. The tabletop is a uniform circular disc, so its mass is evenly spread. That means the center of mass of the table lies exactly at the geometric center. The 3 legs also form an equilateral triangle placed symmetrically around the edge. Because of this perfect symmetry, the combined system is balanced, and the overall center of mass of the table and legs lies at the origin. Now let's prove mathematically that the center of mass lies at the origin. The formula for the x-coordinate of the center of mass, and similarly for y-coordinate, is like finding a weighted average of all the positions. You take each object's mass, multiply it by its position, add them all up, and then divide by the total mass of the system. When we substitute our data into the formulas for the center of mass and x and y plane respectively, notice that the positive and negative terms cancel out. Therefore, the overall center of mass of the system lies at the origin. To find the minimum mass that will tip the table, we must also choose where to place that mass. The best place is at the rim directly opposite a support edge. In our diagram, that's point X opposite side AB. Why? Because placing the weight as far away as possible from the pivot creates the largest lever arm for a given mass, so you need less mass to reach the tipping threshold. When we place an extra mass on the rim, the center of mass of the system shifts toward that point. The table stays stable only if the vertical line through the center of mass falls inside the support triangle. As we add mass at point X, the center of mass shifts until its vertical line reaches edge AB, which is the tipping point. At that instant, the reaction force at the opposite support becomes 0, and the table is just about to lift. The smallest mass needed to make this happen is the minimum tipping mass, and the distance at which center of mass needs to shift vertically from the origin is negative 0.5. We already know the tipping threshold and the existing system mass. In our case, the system mass has its center of mass at y equals 0, and the added mass, mx, sits at position x, where y equals negative 1. Now let's take each part's mass, multiplied by its vertical position, add them together, and then divide by the total mass. So the smallest mass that moves the center of mass onto line AB, and therefore just causes tipping, is 35 kilograms. If you found this explanation helpful, make sure to give the video a like and share it with friends who love physics. Don't forget to subscribe to the channel and hit the notification bell so you never miss our step-by-step breakdowns of advanced problems. Let's keep exploring physics together.